Hello and welcome to this live demo of Beta CAE systems. This video will demonstrate a short introduction to the Ansa API and its capabilities. The content to be discussed is geared mainly for new users. The first tool that we should get familiar with is the script editor, which is a complete editing environment attached directly to the Ansa core functionality. To open the script editor, press the script menu button and select Script Editor. Here we can either start editing a new file or open an already existing one by using the respective options from the File menu. The main part of the window is the editor, while on the right side lies the search toolbar. By double-clicking on a selected function, the respective documentation appears on the Help window. When we press the Run button, the code will be executed and all the appropriate messages will appear on the output window. Also notice that the various Ansa APIs are derived in distinct modules, separating their different functionalities. In the Library tab, we can see a list of these modules as well as the APIs contained in each one of them. The fundamental API of Ansa is the class base.entity. Every entity of the Ansa database, whether it's a node, an element, a property, or any other entity, is actually an object of the class base.entity. In the class's documentation, we can see the attributes and the methods that all those objects share. Such objects can be directly created through scripting, or already existing ones can be retrieved by using the appropriate functions. Now, let's try to retrieve an existing entity from the Ansa database. Let's say a property entity. In order to do that, we will use the function base.getEntity. But firstly, we have to import all the relevant modules. In our case, base and constants. Then we can search the function, and by right-clicking it will appear in our editor window. The first argument of the function is the dec, which is just a constant, depending on the dec that we're working. In our case, constants.nastran. The second argument is the type of the entity. This is a string that can be retrieved from the title of the element's edit card, where it is displayed within brackets. For our case, this string is pshell. The third argument is the ID of the entity. In our case, let's retrieve the property with ID 10. Now this function will return to us a reference to the desired entity. In order to access this entity's ID and name, we can use two of the class's attributes, _ID and _name. If we execute, we can see that the prints give us back the desired results. Apart from the name and the ID, we might also want to acquire more information from the property, such as the thickness value. In order to do that, we should use the method getEntityValues, which takes the dec as the first argument and the second argument an iterable with the labels of the fields that we want to acquire. In our case, the capital letter T. This function will return a dictionary with keys, the labels that we asked, and values, their respective field values. We can also modify the fields of an entity by using the method setEntityValues. Here, apart from the dec argument, we should provide a dictionary with the new values that the respective fields should take. After executing, we can go back to our Ansa database and see that our new thickness value of our property is the integer 2. Apart from acquiring and modifying a single entity, we can also collect massive entities of the same type. To do that, we can use the function base.collectEntities. Let's use this function to collect all the nodes of our model. The first argument is once again the dec constant, while the second argument should be none in order to search the entire database. Now the third argument is the type of the entities that will be collected. In our case, we can see that this type is the string grid. This function will return to us a list with all the collected entities, and we can print its length in order to find out the total number of the nodes entities that our database contains. Another function that is commonly used is the base.createEntity, which is used to create a new entity. Suppose that we would like to create a new node entity. We should provide to the function the grid keyword. And optionally, we can provide some extra information, like for example, the name that our new node entity will take. This function will return to us the newly created object, and by printing its ID, we can confirm that the specified node has indeed been created. Now we can go to the Ansa database, search for the ID of the new node, and we can see that this node indeed exists with the name that we provided. Now let's see a small example to get familiar with the model browser. Suppose that we want to let the user select some elements and then add them to a new part. In order to do that, we should firstly use the function base.pickEntities, which puts Ansa in select mode. Here, we specify that the user will be able to select any element of our database. This function will return to us a list with all the selected elements, and we can print out its length to confirm the total number of the elements that we have selected. This next step is to create a new part by using the function base.newPart and specifying the name of the part. In our case, we will use the string new part. Finally, we should use the function base.setEntityPart in order to add the selected elements to the part entity that we just created. The first argument is the selected elements, and the second argument is the part entity. Now, when we execute, we can see that we get to select the elements. We will select 5 elements. Then we can see that the part has been created, called new part. And the elements that we selected are contained in it. As a complete example, suppose that we want to find and rename all the nodes with x coordinate less than 1600 and then add them to an Ansa set. Firstly, let's create a function to find and rename the nodes. As a first step, we should collect all the nodes from the database. To do that, we will use the function base.collectEntities. This will return all the nodes in a list. Then, we will create an empty list to fill it with the appropriate nodes. We will apply a for loop and examine the x-coordinate of each node. To do that, we will use the position argument, which returns a tuple with the xyz coordinates. The index 0 corresponds to the x-coordinate. So if the x-coordinate is less than a specified value, for our example, that will be 1600, then the next step is to add this node to our empty list by using the command append. Also, we will create a new name for that node, which will contain information about the ID and the x-coordinate of the node. We will modify the node's name by using the method setEntityValues. And providing a dictionary with the key name and value the new name. We will also return the created list. Now let's execute and print the total number of the nodes that we collected. If we go to the Ansa screen and select an appropriate node, we can see that its name has been modified. Now, the second step is to create a function that will add those nodes to a newly created set. Firstly, we should create a new set with the function base.createEntity. The keyword to be used is set. Then we have to use the function base.addToSet in order to add the nodes to the newly created set. The first argument will be the set, and the second argument will be the nodes list. If we execute and go back to the Ansa database, we can see a new set that contains the respective nodes. All those that have x-coordinate less than 1600. During the creation of the set, we can also provide a name for the set to be created. In our case, the name will be myTempSet. We can execute again, and we can see that a second set with the name given has been created and contains exactly the same nodes as previously. However, if we try to execute once again, we will get an error because of trying to create a new set with an already existing name. In order to avoid this error, we can create a small function that will be responsible for appending an ascending integer to the end of the set name and make sure that the set is always created. Our function will execute a while loop, which will finish only when a valid set name is given. This set will be returned, and a call to this function will replace the set creation procedure. Now we have to make some small code modifications to the arguments of the functions in order to provide the set name as an argument of the function. Now we can execute, and we can go back to the Ansa database and see that the set is created with an integer at the end of its name.